Okay, here is the third question. We did it in class. It is also a pretty simple case with an intercept and one regressor, right? And the conditions are given in this way. Okay, so I wanted to show you this thing, but here the difference is only in the previous question I said there are two different ways to uh, to prove this result. For example, we first is using general theorem, or the second possible approach is using just specific assumptions, right? Directly proving from here to there. Or general theorem is using these assumptions to verify the general theorem and then bring the general theorem's result to this one. Both are technically possible, but in this case, the general theorem approach does not work because, as I said in class, we do not assume we need this assumption for the general approach, but there is only one exogeneity assumption. That is the difference, right? So I mentioned it in class. Let me try that again, do that again, repeat that. So to covariance of x and ui is 0. This is the starting point, right? And then we know by linearity assumption ui is yi minus alpha 0 minus beta 0 xi. Okay, plug this into the exogeneity condition, then you get covariance x yi minus alpha 0 minus beta xi. So remember, covariance is linear in each argument. So you can rewrite this as covariance of x, y minus covariance of x alpha 0 minus covariance of xi beta 0 xi, right? Then this covariance is 0 because it is constant, it is not random, so it does not allow any covariance. It does not move, so does not co-move with anything. Therefore, it is 0, and beta 0 is multiplied. It can go out of the covariance, so covariance x y minus beta 0 covariance xi is what we get. That is 0, right? It should be 0. And again, this covariance between x and x itself equals variance of x, right? That's the definition of covariance. Then because it is 0, we may rewrite covariance xi yi equals beta 0 covariance variance xi. Okay, then if variance is not 0, which is already assumption 3, then beta 0 is covariance divided by variance. Proof is done. This is how we prove it. Okay, that was answer to this question. And now we have demeaned random variables. Okay, let's see this. Clear page. We have y tilde equals y minus expectation y, and x tilde, similar definition, minus expectation x. Okay, then what we are going to do here is we have our original equation, and let's take expectation on the original equation. Then remember, we are not removing this. We do not assume it is 0. So the expectation of error term could be non-zero. Does not matter. Let's take the difference. So yi minus expectation of yi equals alpha canceled out beta 0 times xi minus expectation xi. Finally, ui minus expectation ui. Let's try. Then you may rewrite y tilde equals beta 0 x tilde plus u tilde. Okay? Then it answers this question. Pretty straightforward. Now we are going to concern this equation, and we will think about, so let me erase again and restart. yi tilde is beta 0 x tilde plus u tilde. So we wanted to check exogeneity and full rank assumption for this equation. Okay, so exogeneity, but like look at this. This equation, this linear regression model has only one regressor. Even there is no intercept. It does not have any intercept. So exogeneity assumption is simply one equation. If you show this, that is all the exogeneity equation you want, or assumption you need. And the full rank assumption is it's square. So you need to write it this way, but there is nothing to transpose. X tilde is one dimension. So you can simply write it as a square. And for this number to be invertible, that means it is not zero. Whenever it is not zero, you can take the reciprocal. So that is what we have to show. So let's show the exogeneity first. Expectation of xi tilde yi tilde is expectation of xi minus expectation x times excuse me. So ui minus expectation of ui. Remember, this is definition of covariance between x and u, and we already assumed it is 0. So it is implied by, not just implied, it's equivalent to covariance between x and ui equals to 0, right? Mathematically identical, right? And then now let's try this. Expectation of x tilde squared is, again, x minus expectation x squared, which is the definition of variance, right? So whenever this is not 0, that is equivalent to variance not 0, right? So that means the two assumptions here are exactly the exogeneity and full rank assumptions for the new regression equation. So then you may claim the general theorem. From the general theorem, we verified all the assumptions. This is linearity assumption. What we showed here is linearity assumption, and then exogeneity and full rank are implied by the given assumptions. Then beta 0 is expectation in the general theorem. General theorem notation is this, but specifically in our case, this much is simply this guy. And the second part is this guy, right? This is what we have to calculate. And we already know this is variance of x. And following some similar algebra here, we can show that this guy equals covariance between x and y. So as a result, we have covariance x, y over variance of xi. That is beta 0. So what I wanted to explain here is I do not assume expectation of ui equals to 0. It is not necessary, right? Using the t-mean variable trick, we remove the intercept, and still then we could satisfy all the classical linear regression model assumptions, right? The original model did not satisfy this assumption, may not satisfy this assumption, so it does not fall into the classical linear regression model, right? But in the end, if you remove the intercept using the t-meaning technique, then we got this result, the same result, right? They are the same thing. So this implies, I explained what I wanted to say here. Intercept is normalization, right? So error term is normalized to 0. So mean, 0, error, and intercept are just normalization. They just complement each other. And also, from now on, I do not denote intercept. Instead, I will assume everything is mean 0, right? So I will assume that everything is demeaned, then I do not need to bother the intercept to simplify the notation. Okay, this is it.